Hi 242. In this video we're going to finish up section 10.5 by just talking about a couple more derivative rules that we didn't quite get to in class today, but I want to make sure we finish up this section so we stay on schedule. So today in class we talked about the constant rule. We didn't name it officially, but it's called the derivative of a constant, or the constant rule. And then we talked about the power rule. Right? So the constant rule, or derivative of a constant function, is stated to be that if we have a function defined to be like this, f of x equals c, and remember that this means that c is a real number of some kind. Okay, then how do we take the derivative of this function? Well, we notice that because, remember, the derivative is the slope of the tangent line, and any graph of this kind is going to be a horizontal line. And what that means is that its tangent line is horizontal also, so it doesn't have any slope. Its slope is 0, right? So what that means is that the derivative of this thing is always going to be 0. Okay? Good. And the second thing we talked about today was what's called the power rule. And this allows us to take the derivative of powers of x, and to do this more easily than having to do that 4-step process that we saw in class, as well as in our last video for section 10.4. So what this rule says is that if we have a function defined by a power of x, and again here n is can be any real number also. Okay, n can be anything we like. It can be an integer, it could be a fraction, it could be a negative number, it doesn't matter, right? N can be anything we want. So when we have this, then we can say that the derivative here is found by using this rule, okay? And it's not important for us to prove this rule to ourselves. We've noticed that it worked in that example that we did today. But the rule says that we take the power currently that's there, we bring that number in front as a constant, that's that n, and then we subtract 1 from that old power, right? And that's our new power, right? So let's try a couple of examples here just to make sure that we've got these few rules handled. So first, let's consider, this is match problem 2 from your section of your textbook. This is page 528. Okay, so if I have f of x is x to the 6th, let's find its derivative. So remember that we can denote the derivative by f prime of x. That's one of our notations that we have here. Okay, and if we want f prime of x, then how do we take its derivative? This is x to the 6th. This is like x to the n, with n being 6, right? So we can make use of the power rule here. So what I do is I bring that 6 out front as my new sort of number out front, 6x, and then I do subtract 1 from the power. Okay, so that means this is 6x to the 5th. And that's the derivative. That's f prime of x. All right, let's try this on the second one. So we have the function y equals x to the 30th. Okay, and if I want to find the derivative of this, remember we have lots of ways to denote this, but just to practice with the notation, we could write y prime, remember, and that means the same thing, the derivative of y prime. If we had this as f of x, we could have written f prime of x. Okay, the n up in the exponent here is 30, okay, so that means that I could bring that up front, 30x to the 30 minus 1. Okay, so this is 30x to the 29th. Good, and that's the derivative. Okay, let's keep going. There's 2 more examples here. So I have y equals x to the negative 2. Okay, now you may be concerned that this is a negative 2 up here, but remember that I told you that you can use this for any power on x you like, any real number power up there. So we just follow the same rule. Okay, so let's use that notation. Let's use y prime again. Y prime to denote the derivative. And what do I do with that power? Remember that number goes out front, negative 2, x to the, and now I subtract 1 from the power, negative 2 minus 1. Now be careful, negative 2 minus 1 is going to be more negative, right? So that means here this is y prime equals negative 2x to the negative 3, right? It gets more negative. Okay, just be cautious with that. All right, one last one here. So I have y equals x to the 3/2. Again, it doesn't matter that this is a fractional power. Again, the power is able to be whatever we want, any real number. Okay, there was one last notation for the derivative, remember, that I showed you, and that's the notation dy dx, right? So let's use that this time. That says the derivative, okay, when we have y equals x to the 3/2, the derivative will be dy dx equals something. And we can take the derivative of this, again, using power rule, because it's a power of x. So I bring the whole number down in front, 3/2 x to the 3/2 minus 1. Okay, well, what is 3/2 minus 1? That's 1/2. So I write dy dx equals 3/2 x to the 1/2. Okay, and that's the derivative. That's the derivative of y equals x to the 3/2. Good. So those are that's an example of how to use the power rule. If you'd like an example for how to use the constant rule, remember that we can just think about things like this. If I have y equals 15.4, right? That's a constant function. So y prime will equal 0, right? Because it's just a constant. Okay. Derivative of a constant is 0. Derivative of a power of x makes use of power rule. Great. Okay, so let's look at the last two rules we have for this section, and then we'll do a couple examples. Okay, so this one is called the constant multiple rule. Okay, and this one is useful for if there is a constant multiplying a function. So let's, for example, consider this. Let's define a function f of x. Let's say it's found by multiplying another function by a constant. Okay, where c is a real number. Okay, so f of x is equal to c times some expression of x, right? If you want to think of an example of something like this would be maybe, for example, like 3 times x to the third or something, right? There's a number in front of an expression of x, just like that, okay? And maybe if you want more examples, maybe f of x equals 16 times x to the fourth plus 2x plus 1. Okay, that's another example of a constant multiplying an expression of x. Okay, so how do we take derivatives of these things? So what is the derivative of f prime if it's defined to be a constant times another function like this, another expression of x, right? Because that's all this says is another expression of x. Well, let's see if we can make use of our definition of the derivative here if we wanted to calculate f prime of x. And I'm going to do this for in general, right? I'm going to make use of the original starting definition of f of x, not these examples that we've talked about here. Okay, so let's use our limit definitions. This is the limit as h goes to 0. Okay, and remember how we write this. It's f of x plus h minus f of x over h. That's a definition for the derivative that you really need to have committed to memory or learn to put all the parts together to see why it's there. So let's start filling in parts and constructing this and figure out what the derivative actually is. What is f of x plus h? Well, remember, we're just asking to make the input x plus h. If f of x is defined to be c times g of x, then that means f of x plus h is just c times g of x plus h. Okay, because that's how this is defined. If I were to write what is f of happy face, it would be what? I'd take this definition here and I do c times g of happy face. Okay, and that's the same exact thing I'm doing here. I'm just plugging in x plus h instead of happy face. Okay, minus what is f of x? It is c times g of x, constant times g of x, and I divide by h. Okay, well, this may look horrendous, right? But notice that in each of these two terms there is a c. So what I can do is factor that thing out from both terms in the top. C times g of x plus h minus g of x all over h. Okay, and if we think about this carefully for a second, let me erase this stuff over here. Notice that this constant right here is multiplying everything inside. And what can we do with the constant acting inside of a limit? The constant isn't a concern to the limit, right? It doesn't matter. It can come all the way out front. Okay, remember, limits, when there's a constant in there like that, we can just take it right out front. So we have c times the limit, h going to 0, g of x plus h minus g of x all over h. And now hopefully this looks a little bit familiar because we haven't used the letter g before, but isn't this part over here on the right hand side, isn't this a definition of a derivative? Limit h goes to 0, a function with x plus h plugged in minus a function over h. That's the definition of a derivative. Okay, so what this means is that this is c times, this is the definition of a derivative, but the derivative of who? Not the derivative of f, the derivative of g. And how do I write that? The derivative of g, like that. Aha! So what that means is we just found that to find the derivative of f, right? To find f prime over here, it's easy enough to just do the constant times the derivative of g. Okay, and what this means is that if f is defined to be a number times an expression of x like this, right, then the number, the c thing, just kind of goes along for the ride, and then you just multiply by the derivative of what g is. Okay, so let's try an example here to see exactly how this works. Let's take our example up there where we have f of x is 3x to the third, right? Remember, this is 3 times x to the third. So this is like having f of x equals c times g of x, right? It's like g of x is x to the third. Okay, so in that case then, if we want f prime of x, that means that we have to do what? We just take the c, the constant, which for us is 3, right? And then we multiply by the derivative of g of x, right? We multiply by the derivative of x to the third. What is the derivative of x to the third? We make use of power rule. So the 3 comes out in front, x to the 3 minus 1. Okay, this is g prime of x. This is the derivative of x to the third. Okay, so that means f prime of x here is the 3 and the 3 interact in multiplication to be 9. X to the 3 minus 1 is 2. Okay, so this is the derivative of 3x to the third. It is 9x squared because the 3's interact with each other. One's a constant, one comes down because of the power rule, and we subtracted 1 in the power because of the power rule, how it's defined. Okay, great. So let's try one more example making use of the constant multiple rule. I'm going to do a couple of problems from matched problem 4 on page 530. Okay, and so let's see, let's pick a really good one. So here, if we have in part A, we have f of x is equal to 4x to the fifth. So how would we find f prime of x? Okay, so notice that what we can do is, remember, this is 4 times an expression of x. So it's like the g of x thing is the x to the fifth. So I take the derivative by doing 4 in front. It just stays. Remember, that's our c. And what's the derivative of x to the fifth? Apply the power rule. The 5 comes out front times x to the 5 minus 1. Okay, so f prime of x is 4 times 5 is 20, x to the fourth. Okay, let's try B. So we have y equals 1 over 3x to the third. All right, well, let's see. Does this look like we have a number times an expression of x? Maybe if we rewrite it as 1 over 3 times 1 over x to the third, then we'll see that it's actually c times an expression of x, right? This is like c times g of x right here. Okay, so if I rewrite this as y equals 1/3, how can I write x to the third, 1 over x to the third here, right? Because I want to be able to take the derivative of this thing, and so far all we have is the constant rule, the power rule, and this constant multiple thing where there's a number sitting out front. Well, if I rewrite 1 over x to the third as x to the negative third, then I can apply power rule, right? So let's see, y prime, oops, not red. So y prime, the derivative, is going to be what? The 1/3 stays out front as c. And now I have to do what? Apply power rule to this x to the negative third. So I do bring the negative 3 out front, x to the negative 3 minus 1. Okay, so let's simplify a bit. Y prime equals, what happens to the 3 and the negative 3? They cancel, leaving me just the negative sign. So I get negative x to the negative 3 minus 1 is negative 4. Okay, perfect. Great. So let's see. How about just one more? How about we'll do C? So if I have y equals x to the fourth over 12. Your book actually states this as y equals t to the fourth over 12. I mean, does it make a big difference what the letter is here? Not really. Okay, it doesn't matter what the independent variable is if you like. It doesn't really matter. We can take the derivative equivalently either way. Okay, if I wanted to, I could write this as y prime, and I would write this as some kind of a derivative of this thing. I would write y prime over here also if I had t's. The only difference is that if you were to use that dy dx notation, that is for a change in y over change in x, but if your independent variable is not x, if it's t, you can't write dy dx. Okay, that wouldn't make any sense because your independent variable is not x here, right? In this case, the independent variable is t. Okay, so what you'd have to do is instead of writing a dx down in here in the bottom, you would write dt. Okay, so any of those notations would be fine as long as you keep respect to what the independent variable is, as long as you keep that notation straight. You shouldn't be nervous about there being different kinds of letters in there. Okay, so let's actually make use of the t one and just get some practice with using an alternative letter, right? So let's see, if y equals t to the fourth over 12, how can I take the derivative of that thing? So let's see, dy dt, right? That's what we wanted to find because t is the independent variable. Well, I could rewrite this thing so that it looks like a number 1/12 times a power of the variable, power of x or power of t, whatever letter you like to use. So the derivative would just be 1/12 times I power rule on t to the fourth. 4 in front, t to the 4 minus 1. So this is dy dt equals, let's see, 4 and 12 cancel, leave me a 1/3. T to the 4 minus 1 is 3. Okay, great. The last rule that I wanted to talk to you about is the rule that says that derivatives, if we have more than one term for a function, you just move term by term to take the derivative of the function. And this is called the sum and difference property. And this is on page 531 in your textbook. So this is sum and difference. Okay, so let's say that we had a function here, f of x, and let's say it was defined to be an expression of x plus or minus another expression of x. Okay, so maybe something like, if you're wondering what this would look like, maybe something like 3x squared plus 2x. Okay, that would be an example of a function that was defined by the addition or subtraction, maybe, of two expressions of x. So if that's the case, how do we find f prime of x? Well, the rule says that all you have to do is move term by term. Take the derivative of the first term, and then add or subtract the derivative of the second term. Okay, and when you do that, you'll have the completed derivative. So to consider an example of how this is used, let's look at maybe matched problem 5, and we'll just do 2 of these maybe so that our video doesn't get too long. Okay, so maybe in part A, this one's a long one. So let's say f of x is defined to be 3x to the fourth minus 2x to the third plus x squared minus 5x plus 7. Okay, so there's nothing that says we have to have just 2 terms, right? We could have lots of terms, and the rule would still apply. All it says is that the derivative goes term by term. You take the derivative of each term. So to find f prime of x, we just go term by term. Okay, so let's handle this first. What's the derivative of 3x to the fourth? Okay, well, this is going to make use of a couple of our rules. The 3 is just a constant multiple, so it stays. And then I have to do what? Derivative of x to the fourth, which makes use of power rule. 4x to the 4 minus 1 is 3. And then we just go to the next term and we take its derivative, minus, so the 2 is just a constant here, and apply power rule to x to the third, 3x, and then subtract 1 from the power, squared. Now go to the next term, plus, is there a number in front? Nope, so we don't have to worry about the constant multiple rule. We just take the derivative of x squared by power rule. 2x to the 2 minus 1 is to the first, but we usually don't write that, no big deal. Okay, next term, minus, I'm moving to the next line down. 5 is a constant multiple out front. Now we take the derivative of x. Okay, the derivative of x, remember it currently has a power of 1. Okay, so that 1 comes out front, and I do 1 times x to the 1 minus 1, which is 0. Okay, lastly, I have plus. What's the derivative of 7? Well, 7 is just a constant, right? So the derivative of a constant is 0. So our finalized derivative would look something like this. It would be 12x to the third minus 6x squared plus 2x minus, what is x to the 0? X to the 0 is 1, so this is just 5 times 1 times 1. So this is minus 5, and there is no constant term after that, so we're done. All right, let's just do one more, and we'll be done. So we've got y equals 3 minus 7x to the negative 2. So y prime, remember that's our notation for a derivative, Derivative, we go term by term, right? So we start with the first term. What's the derivative of 3? That's the derivative of constant. We've talked about that before. The derivative of a constant is 0. Okay, now this sum and difference rule says move to the next term. So minus, what's the derivative of 7, x to the negative 2? Well, the 7 is just out front as a constant multiple, so it stays. And then I do what? Multiply by the derivative of x to the negative 2, which is power rule. Negative 2 x to the negative 2 minus 1. So y prime is, let's see, what is this? 0 is just 0, so I don't even need to write anything, right? So that can just go away. So let's see, this is minus 7 times negative 2, which is positive 14. X to the negative 2 minus 1 is negative 3. Okay, that takes us through the end of 10.5. Sorry I had to squeeze it in at the end with a video, but hopefully you've enjoyed the video and you can watch it as many times as you like to see how all of the properties and rules for derivatives work together. We'll review these items on Monday.